remember we 3D with study B. Enough respect go to a vet on me. PSK, maison pause delay. You see Judy rock ride the chords fade. Reach from the bottom, discombobable belay.
Okay, so last time I told you about this theorem, which was about bounding the expected length of rows when you do the RSK process or the Pokemon process with random input. And in fact, you can understand everything I'm going to talk about in this video just only with respect to the combinatorics of this RSK or Pokemon process. You can forget everything about quantum if you like. So to remind you of the setup, we have D symbols in the words that we're going to put into our RSK process. These were the ranks of the cards in the Pokemon scenario, and the highest rank has probability P1, the next rank has probability P2, and so forth and so on. And we're going to get a sequence of n cards, or a word of length n, run it through the RSK process, look at the resulting Young diagram, lambda, and this theorem tells you about the expected length of the kth row, and it tells you it's quite close to pk times n, and the level of closeness is 2 times square root n, and you can even add in an extra factor if pk is rather small. Okay, so I'm going to talk about how this is proven using mainly combinatorial tools. So the key lemma is the following. It looks a little bit complicated, but it tells you about the expected value of the sum of the first k rows in lambda versus the sum of the first k sort of target values, pj times n. And it says that the first quantity exceeds the second by something small, just this funny sum of fractions to do with the p's. And this second quantity here, you can think of it as the number of boxes in the first k rows if you were to just compute the normal histogram of your card sequence C. If you took n cards with probabilities P1 through PD and just wrote down the histogram, you didn't do the funny RSK process, and you looked at the number of boxes in the first k rows, here we're comparing it to the number of boxes in the first k rows you get from the RSK process. So this left-hand side kind of bounds the top heaviness of lambda vis-a-vis what you would get if you just made the histogram. Okay, so this is a concrete statement that holds for all n, and you might compare it to this result I mentioned in the previous video by It's, Tracy, and Whittam, which actually only concerned the case of k equals 1, so the expected value of the number of boxes in the first row, which has the nice combinatorial interpretation of the expected length of the longest increasing subsequence in your sequence of cards. So they showed that the expected value of lambda 1 was pretty close to P1n, and the difference was this, again, expression involving the p's and some fractions, and it's exactly this right-hand side expression here, specialized to the case k equals 1, up to an error which goes to 0 as n goes to infinity. So one difference about this is that there's no n going to infinity. This is like a concrete statement that holds for every n. And their proof did not really use anything about the RSK process or the combinatorial aspect of the Pokemon process, if you will. It really just kind of grinded a little bit using the Schur polynomial formula and the Hooke formula for the dimensions of certain representations and so forth. So what I want to explain now is that an important part of the proof of the theorem I showed you is sort of looking into the combinatorics of it. So as an example, I'm going to tell you about the proof of the key lemma just in the case k equals 1. So if we specialize to that case, we're trying to show that the expected value of the number of boxes in the first row when you do this RSK type process is close to P1 times n, and the difference is at most this sum of fractions, Pj over P1 minus Pj. Now, as mentioned, this is to some extent what It's, Tracy, and Whittam studied, and what they showed was that the quantity on the left-hand side here, this difference, tends in the limit as n goes to infinity to this number on the right-hand side. And as I mentioned, they did that by sort of explicitly doing some hacking with the asymptotics of this Schur polynomial and these dimensions and so forth. So it really seemed to heavily involve the fact that you were taking a limit as n goes to infinity. But as I talked about in the previous video, I mean, if you have this kind of limiting statement, it really doesn't help prove a concrete statement like this, because it only these left-hand side and right-hand side are only small once n is bigger than some unspecified number n0, and this n0 may well depend on d, and it may well depend on the difference between the consecutive p's, and in fact, it does depend on these things. So it seemed that their limiting statement, doesn't help us at all in proving this. But actually, by kind of a funny twist, it helps a great deal. once you know one more combinatorial fact. And that combinatorial fact is the following claim. I claim that this left-hand side here, sort of the expected top heaviness of the first row vis-a-vis what it would be in the histogram, is a non-decreasing function of n. So it's an increasing function of n. And actually, once you know this combinatorial statement, you get the key lemma immediately because its Tracy and Whittem show that the limit of this function of n is this number on the right-hand side. So if the limit of this function of n is this number on the right-hand side, and moreover, this function is a non-decreasing function, well, then it simply has to increase to its limit everywhere, and therefore, indeed, it's at most the right-hand side for every value of n. So we can actually borrow the its Tracy-Whittem result, and now it remains to show this claim about the non-decreasing nature of the left-hand side. Okay, so how do we prove this? Well, this is where the combinatorial aspect of the RSK process, the Pokemon process, comes in. So although we're going to be choosing n cards for this claim, let's just choose like an unending stream of cards. I'll call it C, and the card ranks are C1, C2, C3, etc., where each card is drawn independently from the probability distribution P. And we'll imagine doing this Pokemon process I described in a couple of videos ago to these cards as they come in. And therefore, the distribution of the Young diagram after n cards is exactly this lambda superscript n that we're interested in. Okay, so now to prove this function is non-decreasing, I'll just subtract the nth plus 1th term and the nth term and try to show that that's non-negative. So if you subtract the n plus 1th term and the nth term, you want to show it's non-negative, then what you end up needing to show is that this quantity, the expected value of the difference between the number of boxes in the first row at time n plus 1 and at time n, well, that should be at least P1, the probability of the highest ranked card. Okay, so now let's consider this expectation. Well, these two quantities are usually the same. It's either 0 or 1. It's 0 if the kid 1's deck size does not increase from the n plus first card, and it's 1 if kid 1's deck size does increase from the n plus first card. So this difference is the expected value of the indicator that the n plus 1th card that comes in actually increases by 1 the deck size of the oldest kid. Okay, so that's the expectation of an indicator. So it's just the probability of the event that the n plus 1th card increases kid 1's deck size. Now, if you think about, if you remember back to how this Pokemon process worked, well, if the kid 1, the oldest kid, got some, high-ranked card like a number 1 or a number 2 or a number 3, they would keep it, but would have, of course, by this household harmony rule, would have to give up their next highest ranking card to the second kid. And in this case, the size of their deck would not increase. It would stay the same. But there is one circumstance in which kid 1's deck size definitely increases, and that's when the kid gets the worst card, the card of rank D, because then kid 1, he doesn't have a worse card that he's obligated to donate to the second kid. So if this event occurs, that the n plus 1th card is of rank D, then indeed the kid 1's deck size increases. So that gives us a lower bound on this expectation. And by definition, this probability is exactly PD. So this almost looks good, except that we were trying to show that this expectation is at least P1, the largest probability, not that it's at least PD, the smallest probability. But now you can remember this funny fact about the Pokemon process, the RSK process, which is that it's actually invariant. The number of boxes in each row, the distribution of the box lengths, is invariant to permuting the P's. And therefore, if you can prove this with PD, by permuting the P's, you can also prove it for P1. And so that lets us put P1 on the right-hand side and actually completes the proof of this claim. Okay, so if you've seen that, it's a little exercise. If you want to follow along at home, you can try to prove a similar claim that the expected number of boxes in the first k rows of the Young diagram minus the expected number of boxes in the first k rows of the plain histogram is also a non-increasing function in n. And that helps you prove the general form of the key lemma, not just this version about the first row, which we talked about. Okay, so this is the key lemma that we proved. Now, it doesn't completely complete the proof of the main theorem they were trying to prove. And you can see there's already some problem in trying to use this key lemma to prove the theorem. For example, this quantity on the right blows up to infinity if two consecutive P's, let's say, happen to be equal. And, there's no reason they couldn't be equal according to the hypotheses of the theorem. So if you want to deal with the blowup that occurs if, let's say, two consecutive p's are equal, what you can do is shift a little bit of the probability mass around. Okay, so shift some of the probability mass from the p's to prevent them from being exactly equal and allow you to use this key lemma. But of course, once you do that, you have to understand how shifting probability mass around affects the distribution of the Young diagrams that you get when you apply the Pokemon process. So dealing with that and getting the appropriate results involves proving what we call the coupling majorization theorem. So this is a one coupling theorem about the dynamics of the Pokemon or RSK process. So let me tell you a little bit about that theorem. Okay, so the setting for this theorem is imagining the Pokemon process or the RSK process applied to two different sequences of card probabilities or symbol probabilities, P1 through PD and Q1 through QD. And let's assume that P majorizes Q. And the meaning of this terminology is that all the partial sums of the first few P's exceed or are equal to the corresponding partial sums of the first few Q's. So in some sense, the histogram of the P's is more top-heavy than the histogram of the Q's. So under this assumption, the better cards or the earlier ranked cards are more probable under P than under Q. And based on how we expect these Young diagrams to behave, we might feel that makes the associated Young diagrams that you get when you use the distribution P, let's call that lambda, we might expect that to be also more top-heavy than the Young diagrams you get mu when you use the Q probabilities. And this coupling majorization theorem exactly says that there's a probabilistic coupling between the P-distributed Young diagram lambda and the Q-distributed Young diagram mu, such that under this coupling, lambda majorizes mu in the same sense that the partial sums of lambda exceed those of mu always with probability 1. And the proof of this theorem is a moderately involved combinatorial bijection proof. So if you take a look at the paper, this is the theorem that you eventually use to prove this coupling theorem, and it's a kind of fanciful looking combinatorial bijective proof. But this is an extremely natural statement, I think, and therefore, maybe as a little open question, I can ask whether somebody out there can come up with, a truly simple proof. Because, as I said, this majorization theorem is very natural looking, very believable looking. Okay, so let's go back to this main theorem that helps us analyze quantum state eigenvalue estimation algorithms. And you see, this key lemma does help us prove things about the sum of the first few lambdas being not too big. But if you look at the statement of the theorem, it involves proving things not about sums of lambdas, but just one particular lambda, like in the middle of the Young diagram, lambda k. It also involves both lower and upper bounds. So to prove lower bounds on some particular middle row, like lambda j, the way we do it involves proving upper bounds for, subsequent k's, rows that are bigger than j. And to prove upper bounds for like some middle row lambda k, and not like in the key lemma for like the sum of the first few k's, involves a second majorization theorem that was proven by John Wright and me, which we call the lower rows majorization theorem. And I'll tell you a little bit about this theorem, but I should say that it has a proof that is not very natural. It's quite intricate and strange, and we had a hard time understanding it ourselves. So if you want a little open problem on the subject of combinatorics here, just come up with any proof at all that seems natural to you, and I'd be happy to see it. Okay, so let me explain what this lower row majorization theorem is about, and it concerns how lower rows of this Pokemon tableau evolve throughout the process. So if you might remember, as I'm dishing out these Pokemon cards to my kids, their current decks might look like this, and perhaps I buy them a new card, and let's say card rank number 1 comes in, kid 1 snatches it, being the biggest kid. By the law of household harmony, he has to give up his next best card, which is this 3, so he puts it out there. Kid 2, of course, grabs that, and by the law, he has to give out his next best card, which is this 4, so he puts it up for grab. The next biggest kid, kid 3, grabs that. And kid 3 doesn't have a worse card than that 4, so he just gets to keep it, and the process for this card stops. Now, actually, let's rewind a little bit to the point where kid 2, had just gotten this 3 and was about to pass out card number 4 to kid 3. So if you think about how this goes, in some sense, kid number 2 sort of acts like a dad himself to kids 3 and kid 4, in that, as time goes on, kid 2 dishes out cards to kids 3 and kid 4. In particular, kid 2 only ever dishes out 3s and 4s because 1s and 2s are always kept by kid 1 and kid 2. So as time goes on, kid 2 sort of in a paternal fashion dishes out some 3s and 4s to kids 3 and 4. And let lambda sub 3 plus be the Young diagram resulting from the cards that kid 2 dishes out. And this is just really the lambda 3 plus is exactly the shape of the Young diagram you get in the overall process in rows 3 and beyond. So this is what you need to study if you're interested in studying the number of cards in the let's say third row, some middle row like the third row of the Young diagram. Now, on one hand, you can consider that, which is what actually happens, but you might also consider a counterfactual scenario. So, run the process for a while and imagine the cards that kid 2 dishes out to kid 3 and kid 4, and imagine what Young diagram would have resulted had those cards been directly handed out by the dad to kids 3 and kids 4. So whatever cards kid 2 would hand out in the process, imagine the dad immediately handed those out to kid 3 and kid 4. Well, you'll get a different Young diagram potentially because they're handed out in different order. So we'll call that Young diagram mu. And the lower row's majorization theorem is just this, that the lambda 3 plus majorizes mu 3 plus. So somehow the version where kid 2 is playing the role of the dad is more top-heavy or beneficial to the older kids than mu 3 is. So maybe it's a father knows best kind of situation where it's fairer when the dad hands them out. Okay, and so this majorization theorem lets us reason about the behavior or the number of cards in, let's say, an interior row like lambda 3. Okay, so that's, I guess, all I'll say about how this crucial theorem is proven. And I'll just remind you that you can use this sort of very refined information about the expected lengths of the Young diagrams that you get from this Sure-Weil process to get a very sample-efficient learning algorithm for the eigenvalues or probabilities P of an unknown quantum state. So if you use this idea of taking lambda, normalizing the row lengths by n to form like a vector of estimates, p hat 1 through p hat d, you can use this theorem to show that p hat is very close to p. They're not just close in L1 norm or total variation distance, but even this very stringent measure called chi-squared divergence. And the closeness is at most d squared over n. And as a consequence of that, if you are able to do your quantum learning algorithm with a number of copies n, which is noticeably bigger than d squared, then you will estimate the probabilities p of that quantum state very well. And one great open problem about this result is whether it can be improved. So it's known that this particular natural estimator, p hat, the empirical Young diagram estimator proposed way back by Rnitsky and Sadowski, cannot be improved. It's not a good estimator unless n is at least as large as d squared. However, it is possible that some other algorithm that hasn't been previously considered could do better than d squared. And actually, not to give away too many of my secrets, but I strongly believe this is the case. I really expect and hope to see somebody prove that you can estimate the eigenvalues of an unknown quantum state very well with a number of samples that's little of d squared, subquadratic. Okay, the last thing I want to tell you about and to set up the final video in the series is this. All of this has been motivated by the task of, learning or otherwise studying the properties of an unknown quantum state, a quantum die. But a quantum state rho has not just the eigenvalues or probabilities p1 through pd, but it also has these eigenvectors u1 through ud. So, the quantum state is like a probability distribution over an unknown orthonormal basis, u1 through ud, of d-dimensional space. And so far, for like all these first, half a dozen videos, we've only been talking about learning the p's. But of course, we want to do typically, full quantum state tomography, so we also want to learn the u's as well. Well, all of our work on learning the p's has not been wasted, since the very first step of the known algorithms for learning the whole quantum state involved first learning the p's. But not only that, the algorithms for learning the p's themselves play a fundamental role in the analysis of the learning of all the vectors u. So the main theorem here, first proved by Ha, Harrow, G, Wu, and Yu, and proven in alternate form by John Wright and me, is that there is an algorithm, an estimator, that produces an estimate of the whole quantum state, rho hat call it, which is close in an appropriate distance called trace distance to the unknown quantum die rho, with error that's somewhere around d over square root n. And if you want this to be small, then again, n just needs to be quadratic in d. So it says that once you have quadratic in d many samples, not only can you estimate the eigenvalues well, but you can even estimate the entire quantum state, including the eigenvectors, very well. And here it's actually known, it was proved by Ha et al., that d-squared samples are necessary for any method of learning an entire quantum state. And that's somewhat natural, because if you think about it, these vectors are d vectors in d dimensions, so they're kind of defined by d-squared numbers, so it seems quite logical that you would need at least d-squared samples to learn them well. As I said, though, the analysis of this learning algorithm that learns the quantum states vectors as well, it too relies heavily on this key lemma, and not just for learning the eigenvalues, but even the analysis of getting the eigenvectors right, the u's right, also again relies on this key lemma. And as I mentioned, it also starts out just by analyzing and estimating the eigenvalues of the quantum state. So these are important ingredients even for learning the u's. But as for the final analysis, which I'm going to save for the final video, estimating the eigenvectors requires a whole other ball of representation theory wax. We're going to have to study the representation theory of the general linear group in order to make progress on that. So we'll save that for the next video.